Well, I'm worried that this video might get a little bit long-winded, and I'm going to make you turn it off right now. Because I'll say this is only if you really want to understand acids and bases, and if you're planning on going into organic chemistry after Gen Chem 2, yeah, this will be really important. I mean, you'll talk about this a lot. And it relates to what we're talking about now with acids and bases. So here goes. First of all, a couple of preliminary slides reviewing some things we've already mentioned. There are different definitions of acids and bases. Here are three of them. The most important one for an organic chemist, and perhaps the most versatile definition, is called the Lewis Lewis definition of acids and bases, where we think about electron pairs of electrons being accepted or donated. If they're donated, it's called a base. If they're accepted, we say that the acceptor is a Lewis acid. More on that soon. Also, before we get going, we define the p function as the negative logarithm function. So pH is the negative logarithm of the hydrogen ion concentration. pOH is the negative logarithm of that numerical molar concentration. To go backwards to get the H plus from the pH, I take 10 to the negative on this side and 10 to the negative on this side, and yeah, so 10 to the negative pH gives me the H plus concentration. Likewise, we do the same thing with Ka and Kb. The pKa is the negative log of the Ka, and the pKb is the negative log of, and the p of the smiley is the negative log of the smiley, or whatever number you might have. You could take the negative log of it. Whether or not that's useful is a different story. Also, you remember, don't you, that the pH plus the pOH is 14, which comes from the dissociation equation and constant Kw for water. Likewise, it's true. Did I write this down? I didn't. Maybe later I did. Likewise, the pKa plus the pKb for a particular acid is also 14. I should say, the pKa for a particular weak acid and the pKb for its conjugate base, the sum of those two equal 14. So for vinegar, with the constant of this, which is easy to look up, an organic chemist would often just take the negative log of that, call it the pKa of vinegar, 4.74. Turns out that the stronger your acid, the lower your pKa value. There are some species that can act like acids and bases. I think I threw this in as a demonstration once, twice. I don't know if I did it for you guys or if I will do it for you guys. Feel free to ask. I'm pretty sure I've done this one down here. The Lewis base is the ammonia with the lone pair on the nitrogen. The Lewis acid is the HCl. Let's see. Yeah, the nitrogen with the lone pair donates that lone pair to the hydrogen, allowing the extra electron to be left behind on the chlorine to become chloride. And so this is the Lewis acid-base reaction framed in this jargon, in this context. Bronsted Lowry, how'd that get in there? I should delete that page from a PDF of this. Let's talk about strengths of acids and bases for a second. Have you memorized your strong acids? That means they pretty much dissociate totally in water. So Hi, HBr, HCl, HNO3. Okay, they're strong acids, but you know what? That means the NO3 minus, or the chloride, or the bromide, or the perchlorate. Those are all very, very, very weak bases. As a matter of fact, we say they're negligible base properties in water. Indeed, potassium iodide, sodium iodide, sodium chloride, not acidic or basic really in water at all. So the stronger your acid, the weaker its conjugate base, or the weaker your acid, excuse me, like HOH is water, I could say that's a weak acid. In a sense it is. The conjugate base is OH minus, and that's a strong base. So the weaker your acid, the stronger its conjugate base. For the oxygen-containing anions that create acids, we find that the species, atom, whatever attached to the oxygen at the center of the polyatomic ion ends up having an increasing oxidation state as the acid becomes stronger. So here's HOCl, HOOCl, or I don't know how I want to say that, HClO, HClO2, HClO3, HClO4. The more oxygens you have attached to that central chlorine, the more able they are indeed to share that extra negative that might be left behind when that hydrogen leaves. So this is a strong acid, and this is not such a strong acid. Oxidation state kind of describes the tendency of that central chlorine in this case, or it works with manganese or chromium or anything, metals and nonmetals. Tendency of that to, leaving lost electrons. The more oxygens it has surrounding it, the more electron withdrawing they are, and the higher the oxidation state. It works for this one as well. Like if I had an oxidation state of -1 and 0 and +1, and this would actually probably be +2, it gets increasingly, the strength of the acid becomes stronger. That's redundant. The ability of the hydrogen ion to leave and leave behind the negative whatever increases with increasing oxidation state on that central atom of the polyatomic oxy anion. So just to reiterate Lewis theory, electron pair acceptors are the acids, and the bases are electron pair donors. So looking at some equations, nitrogen is famous for having a lone pair, and it always donates it to the Lewis acid. So in this case, water is the Lewis acid, ammonia is the Lewis base. You could say the same thing about the Arrhenius definition. I mean, you can use that equation, that reaction, but there are many other reactions where you can't use anything other than the Lewis acid-base theory to explain or rationalize how that could be an acid-base reaction. A lot of times organic chemists draw arrows saying where the electrons go. These electrons are kind of pushed over onto the hydrogen. Then the electron pair that was in the bond here gets pushed over onto the oxygen. And this is the OH minus ion. So this would be the base, this would be its conjugate acid, this would be the acid, this would be its conjugate base. That kind of Bronsted-Lowry definition of acids and bases are heavy into conjugate pairs, but it's also important to think about that same thing in the Lewis theory. HBr, I know that's an acid. This could be an acid or it could be base, but I know HBr is a strong acid, so it's going to transfer its hydrogen on over to one of the lone pairs on the hot water, and I could say therefore the water functions as a Lewis base because the lone pairs on the oxygen attract that. Oh, there it is. Lone pairs on the oxygen attract that hydrogen, allowing that bonding pair to be left behind on the bromine. Bromine becomes bromide, yada yada. And of course water can be a Lewis acid and a Lewis base depending on if it loses or gains a hydrogen, and it'll even lose and gain a hydrogen amongst itself. Interesting, as always the case. BF3 or BH3 or boron, try whatever, that means 3 of fluorines, 3 hydrogens, 3 whatevers. Boron's famous for not quite acquiring its octet. 2, 4, 6 is the number of valence electrons around the central boron here. And so because it's electron deficient, it's also looking for more electrons. So it's an electron pair acceptor, and something like this could be an electron pair donor. So this would be a base, and this would be an acid. Interesting. I don't see when I see BF3 or BH3, I'd see no hydrogen listed first. I see boron listed first. So I wouldn't necessarily think, according to the Arrhenius definition, it is an acid, but it certainly can accept lone pairs. So yeah, it can force a reaction. Or same for BF3 or BH3 and ammonia. The lone pair on the nitrogen can be donated to the boron to help complete its octet. Oh yeah, we're getting somewhere. Man, I have a lot of slides here. With larger, more complicated organic structures like this morphine molecule, We see different parts on the molecule with lone pairs on the oxygen, for example. Also hydrogen on the oxygen, and the nitrogen with a lone pair. The sites that have extra electron density, like the lone pairs, could be basic. You could argue that this oxygen has a lone pair that could be a basic site, but if the hydrogen is attached to an oxygen, then something could take that hydrogen away, and that lone pair is left behind on the oxygen. And so in a sense, if this is an acidic site, but right next to it is a basic site. Oh Lord. Oh yeah, it says here the pi bond, so that ring, you might think that double single, double single, double single in the benzene ring would also be basic, and in some contexts perhaps, but that benzene is just so darn stable. General acid-base reaction, so the Lewis base has a lone pair donor, lone pair electron pair donor, electron pair acceptor. So this is my Lewis acid, conjugate base, Lewis base, conjugate acid. Here's an interesting one. Whoa, NH2 minus. Man, that's got to be a strong base. It's seriously looking for some electrons to push off onto somebody. So it pushes it off onto this hydrogen, acquiring the extra hydrogen to become ammonia. And this water certainly becomes OH minus. This is an alcohol. Even in some contexts, alcohols, the lone pairs on the oxygen, could be attracted or could be donated to the hydrogen, pushes the bonding pair pushed over onto the chlorine to become chloride. When you first see these arrow pushing things, it's like, what in the heck are you talking about? But I guess the sooner you see it, the more comfortable you are the next time you see it, and you're like, oh, okay, I've seen that before. I wonder, okay. Acidity constant, yeah, we're used to that. So Ka describes the strength of the acid. If it really is in water, yeah, sometimes we'll include water there, but that's actually honestly rarely done. So the pKa of a weak acid is large. The pKa of a stronger acid is smaller. The pKa of a stronger acid still is smaller. The pKa of a strong acid might even become negative. So lower the pKa, the stronger the acid. You could check that out by taking the negative logarithm of several Kas for increasingly strong acids. Interesting. We could say that, what am I saying here? Oh yeah, so I'm saying if this could possibly occur where this hydrogen is donated to this NH2 minus, there's a Ka associated with that. And if this could possibly happen on this side where where one of these hydrogens is donated back to this crazy looking ion, it could possibly go back this way. So there's a Ka for this going left to right, which is kind of small, 10 to the negative 38, that's super small. And there's a Ka for this forward process where this hydrogen is transferred, and that's also a small number, but it's larger. So in this sense, we're not saying that we're not at equilibrium. We're saying that probably we have more of these species than we have of these species. And because this is a larger number, even though it's very small, it's a larger number than this. Sometimes we use the uneven equilibrium arrows to show the tendency of equilibrium to be favored one way or another, not to say that we haven't reached equilibrium yet. As I go left to right in the periodic table, the pKa decreases for hydrogen bond carbon, hydrogen bond nitrogen. What's the likelihood that hydrogen comes off? The answer is more and more likely as the pKa gets smaller, describing increasing acidity. So HF is a lot stronger of an acid than HOH, for example. On the other hand, when I go down the table, fluoride, HF, is hydrofluoric acid, is a weaker acid than HBr. It turns out if my ion is larger, my negative ion is larger, it can better distribute the negative charge in that space. Because Br has, 2468 lone pair, 2468 electrons, 4 lone pairs, and they're all negative, and they're all trying to get away from each other, and they can do that more comfortably if the ion's larger as opposed to if the ion's smaller. So HF is a weaker acid than HBr. Okay, so if you have two pKa's, again, choose the smaller one. The smaller one's the stronger acid. So I guess this is more likely to lose its hydrogen than this one. And the answer is the fluorines. Why? What? So if I put fluorines on this other end of the organic acid, then that will allow, the fluorines are very electronegative and they draw electrons towards themselves. So they pull electrons away from this region over here and kind of mellow out that intense negative charge. That's what allows this weird looking thing to be a stronger acid than this weird looking thing, because this is kind of like an alcohol, isn't it? No, it totally is an alcohol. Is the hydrogen likely to leave? Well, if it does, it leaves behind an intense negative charge on this oxygen, which the carbons can't really help share that much. So that's how we argue for stronger versus weaker acids. Whatever's left behind as the hydrogen leaves must be stable. Don't go that far. Here's a carboxylic acid group. That's famous for being acidic. This is vinegar. So if that hydrogen can leave, if the hydrogen hopes to leave, these oxygens remaining behind in some kind of resonance structure must be able to share that negative charge. And indeed, resonance structures can share negative charge a lot better than non-resonance structures. That's why this is a stronger acid and that's a weaker acid. Here, I said that again. If the negative charge can be shared or delocalized, or as even including resonance structures amongst the remaining whatever, then your organic species can be a stronger acid. Oh yeah, so here's the resonance. If the hydrogen leaves, it creates this, the resonance structure you studied in Gen Chem 1. We talked about bonding and the Lewis theory of bonding and the necessity to describe hybridizations. Should we ask this question? Which we already did, didn't we? We did. Which of these two is the strongest acid? It'll be this one because it has two oxygens to share that extra negative charge. This one has only one oxygen. But if I put some fluorines over here or some chlorines or something, that could actually help this be a stronger acid. Examples of Lewis bases. Okay, anything with extra lone pairs, the negativity, lone pairs. And there's the extra, I don't see any lone pairs here, but there is that unused p orbital that was used to form a pi bond. So pi bonds by themselves have extra regions of electron density that can react and be Lewis bases. Again, Lewis acids, some kind of region that's looking for some extra negativity. Aluminum can actually form complexes or structures that are also somewhat deficient, like boron. Electron pair acceptors. So if my boron or my aluminum only has 246, that's not the octet, and so they really can enter into some extra bonding. If I'm yawning, you guys must really be yawning. Are you still awake? Let me scroll through some of these. You can look at some of these at your leisure. I don't think there's anything. Oh, new vocabulary. Yeah. Another name for the Lewis base is the nucleophile. The nucleus is positive, so if I'm a nucleophile, I like positivity. So if you're negative, you like positivity. So this Lewis base is also called a nucleophile. Remember that. And it's attracted to the positivity of this bizarre positive species. Electrophile, on the other hand, electrophile, electron loving. So if I am positively charged or have less electrons than I think I should, I would be attracted to the lone pairs of the Lewis base. Same for the aluminum trichloride structure, or boron trifluoride, boron trihydride. Pi bonding is famous for being a Lewis base. Electron deficient hydrogen atom. So I guess they're calling that electron deficient. So this is a Lewis acid. This is looking for some negativity because the chlorine's hogging all of it. Interesting. Lewis base, Lewis acid. Lewis base is the electron pair donor, so it donates it to the hydrogen, forming an extra new bond, kind of breaking that pi bond. We can look at any number of bizarre structures and say where the Lewis acid sites, where the Lewis basic sites. where would the base or a base B be likely to attack? So a Lewis base would look for regions of electron deficiency or hydrogens attached to oxygens, especially hydrogens attached to carboxylic acid groups. So choose this one. I would choose that one. I don't know. Again, that benzene ring is pretty stable. I know. Well, it's a lie. Yeah. Well, shut up. There we go. There's some electron pushing for that one. Well, I gotta finish soon. Where would a base attach itself on this? Oh, that's too far, and now I'm going back the other way. What? Lord, I'm sorry about that. Here we go. No, here. No, here. Yeah, right. Um, so where would this base be likely to attach? It's a Lewis base. It's looking for positivity. Would that be here on the lone pairs of this oxygen? Or what do you think? Maybe here, right? With a Roman numeral. It might actually attack here as well in some cases. But I'm going to say probably the positivity is here. And in some cases it could even be here, believe it or not. That carbon has diminished hybridization, sp2 hybridization. Remember that from Gen Chem 1? Lord. What about this one? Oh my gosh. Lone pair, 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 lone pair. Basic. Lewis acids are electron pair donors. Looks like a basic. Caffeine's a basic molecule. How would you increase the solubility of the caffeine water molecule? How about you just add some acid to it? If I added an H plus here and or here and or here and or here, that would increase the charge on the molecule and make it a charged species and make it more soluble in water, for one thing.